Okay, so this being our last lecture, I'm going to recap the semester and also, you know, go over the material that's going to be on the final exam. So, what have we covered so far? Um, we covered Lab 1 covered a simple CPU. We wrote an emulator for it. We had a few quizzes about how how the compiler might use those instructions to implement. Let's see. We also talked about the C programming language. And so, our quiz was about how you might implement a very simple line of C code with a CPU like that. Um, okay, we talked about the stack frame, how the stack allows us to represent all of the non-global state of a computation. When we're in a specific function, our local variables have a place on the stack, our return address and our arguments have a place on the stack. The local variables for the function that called us have a different place on the stack, and everything's reentrant. If you have a recursive function, then each invocation gets its own stack frame until you run out of stack. Like everything else, if you run out of memory, well, things stop working. We talked about address translation, both very simple and more complex methods of address translation. And this led us to more complex CPU hardware that had a user and a supervisor mode, so that we could have programs which didn't have the same privileges as the operating system. And so the operating system is able to manipulate the address translation hardware, and your own code. If you write a C program, if you go in and edit it to use specific instructions and so on, you still can't change that hardware and escape the address space that you've been given by the operating system. And that brings up a you know, a design pattern or a pattern you'll see through, in this and other systems areas where you implement protection by translation. If you have a translation if all of the accesses from a lower privileged system are translated before before the actual, accessing the resources themselves, then you can protect things by just not putting it in the translation table. So if process A has a particular page of memory, that memory gets put into the translation map for A. Process B can't access it because it's not in B's translation map. We spent a decent amount of time looking at page faults and how we can use page faults to how we can use page faults to load things on demand into memory, how to allocate memory on demand, how to copy memory on demand. Another couple of principles that get used in a lot of computer systems. One is this idea of fast path versus slow path. So the hardware has a fast path, to translate addresses. If it's in the page table, then if you access that address, the hardware will retrieve that mapping from the page table, and then it'll actually get loaded into an even faster hardware path. There's also a slow path that gets triggered when something isn't present in the fast path. In this case, if we're demand loading, we start out with pages that aren't filled in the page table. We take page faults and we can allocate memory and read it in at that point in time, and then we install it into the fast path, the page table. The other general principle there is lazy operations that, in each of the cases with page faults, we were deferring doing some operation. We told the application, oh, we allocated a big chunk of memory for you, but we didn't allocate it. Instead, we wait until they actually access the memory. Then we allocate it and pretend that it was always there. We tell the application we've loaded a file in from memory. Again, we don't do it. We take a page fault and read it in then when they get around to accessing it. Similar for copy on write. We basically promise the application that we've copied something, but we don't do any actual copying until there's a write to one of the pages. The reason that these lazy operations get used a lot is because they're efficient if the application asks for too much. And it very often asks for too much. When you do a fork, the semantics say that you copy the entire parent process address space. Well, most of the time you execute a Sorry, I forgot to recharge these. So, and so, and yes, we have multi-core CPUs nowadays, so you can run a few threads at the same time on the same CPU. But if you were to look at Task Manager or Activity Monitor, you'll see that there's, probably 100 different threads or more across different processes on your laptop right now. And so those are the mechanisms used to switch between them. That's right. Lab 2 was the shell, and Lab 3 was the threads. Um, in Lab 2, we did a simple shell, and we saw how, the Unix shell is just another program. There's nothing magical about it. And, it uses, and Unix provides the fork and exec mechanisms to, to create a child process, which is a duplicate of the parent, and then to replace whatever the current process is running with, the with a specified executable file, with the program from that file. And we saw how we were able to redirect I/O. And the reason we can do that is because there's, a well-known file descriptor for standard input and another one for standard output. File descriptor 0 is standard input. So if you close file descriptor 0 and replace it and, do the, open, dupe, and so on trick to create a file descriptor 0 pointing somewhere else, whether it's a file, reading from a file, reading from a network connection, a physical device, whatever, then the program that you execute, when it reads input, as long as it's just reading standard input, it will read from that stream or file or device or whatever. And so that's the key thing about Unix I/O redirection, is that, it's based on applications all performing input and output the same way, that you read from standard in, that you write to standard out. That way, for instance, it's easy to have shell scripts because, the shell just, reads input from a file rather than, it's easy to pipe output from one program into another program. In each case, as long as the applications conform to those same conventions, we can patch things together into pipelines and so, redirect input and output in ways that let us, that are actually quite powerful. All right. So concurrent programming we saw how multiple threads modifying the same data simultaneously could cause all sorts of problems, because our code is, the way we write code, the way the semantics of our programming languages, the way we do everything is based on this idea that, if your data structure is in good form here and you have a transformation that, then this transformation will transform it into, a good form at the end. But you rarely, it turns out it's often close to impossible to ensure that that data structure is well formed at every step of the way in the middle. In the simplest case, we saw how basically part of the data structure moved from memory into a register while we operated on it. And then, we wrote it back out. And if two threads did that at the same time, the work of one of the threads might be lost. More typically, you do something bad with pointers, and one of your threads ends up crashing with a null pointer. But in general, it's bad. So we talked about mutexes, mutual exclusion locks. These are for protecting data. If you're careful to always lock the same mutex before modifying a particular piece of data, then you'll never have two threads modifying it at the same time. And then unlock when you're done. Sometimes you have to prevent threads from reading that data while you're modifying it. That's common in objects that have lots of pointers, like linked lists and so on, where you might accidentally hit a null pointer while someone else was modifying it. So you'll have to lock the same mutex before observing the data structure as well. And, much as we would love some way to do this magically, mutexes only work because we lock and unlock them in the right places in our program. If you have two threads which are modifying the same data and you didn't realize that, and they're locking different mutexes, well, that's not good. It won't help you at all. And I guess one way to look at what mutexes are doing is that if you have an operation that's surrounded by locking and unlocking a particular mutex, then that operation is atomic with respect to any other operations that lock the same mutex. If two threads try to do this at the same time, one of them will happen first and complete, and then the other one will happen. We don't know which one, but we're guaranteed that they won't happen at the same time. That this operation is indivisible by any other operation that locks the same mutex. You can think of it as happening at a single point in time with respect to those other operations. We saw deadlocks, which the best way to think about deadlocks is the idea of lock ordering, that, you know, the key signal that something may, you know, that there may be a deadlock in a piece of code is that you see one piece of code taking lock A and then lock B, while another piece of code takes lock B and then lock A. And if, you know, the phase of the moon is just right and your timing lines up, you may end up with one thread holding A trying to get B, and the other thread holding B and trying to get A. And there's no way to fix that. That program is stuck and it has to be killed, because the only way to release either of those locks is for execution to continue past the call to lock that it's blocked on, you know, do whatever it was doing, and then execute the unlock instruction. And that's not going to happen. The OS can't fix it because that would involve violating the mutex guarantee. It would mean allowing two threads to hold the same lock. So you know, deadlocks are, you know, well, okay, so that's deadlocks. So where mutexes are for preventing certain behavior, you know, we don't want this thread and this other thread to be executing these certain pieces of code with a certain, you know, data object at the same time. There's an entire universe of program behavior that's okay, but there's some specific things that could corrupt our data, and we use the mutex to forbid them. Condition variables are kind of the opposite. We want to synchronize the behavior of different threads. When we put something into a queue, we want another thread to wake up and start processing it, for instance. And so, you know, and hopefully you'll remember that condition variables aren't variables. They don't have a value. They're just a thing like a mutex. Okay, so if we have a Boolean predicate, and because we're accessing that predicate from multiple threads, you know, by predicate, I mean any, you know, well, for instance, you know, Q is not empty. That's a predicate. It's got a truth value. It's something that we're waiting for. So this is the equivalent of wait until P, and now we have this section of code here where we know that P is going to be true. We've waited until the condition P is true. And the only reason that works is whenever we have a piece of code somewhere that makes P come true, we signal the mutex. So in the case where we had worker threads waiting for work on a queue, they're waiting on the condition that the queue is not empty. So if we put an item onto the queue is not empty, so we signal the mutex. We signal the condition variable. And that wakes up a thread which can then read an item of work off of the queue and and go off, do the work, and then go back and wait for another item of work. Much like mutexes, everything relies on putting this into your code in the right place. If you forget to signal the condition variable somewhere, then this won't work. We'll wait until most cases of P, but not all cases. And so eventually you'll find yourself with a thread waiting even though there's something on the queue because you put something on the queue and forgot to signal a mutex or something like that. Basically, I will say that multi-threaded programming is a pain. There's a lot of environments that go to a considerable amount of length to insulate you from it. For instance, frameworks. I think there's a decent number of frameworks in Java where there may be a bunch of threads that get, say web requests coming in, but then each thread invokes your, execution function, and you don't see the fact that other threads are active at the same time. It handles all. So, to the extent that you can isolate the multi-threaded handling into, a framework above code that doesn't have to worry about it, that's great. The example I keep giving of a work queue, the reason that typically the workers don't have to worry about multi-threading because you gave them a single data object that contains, the work that they're supposed to do. And so as long as those chunks of work aren't, tied to each other in some way, it can go off and do its own thing and not worry about the fact that, other threads are running. It's got its local variables. It's got a structure with the, work to do, or in C++ or Java, it's quite possible it was just all passed as arguments to a function. C is limited that way. So I guess that's, so the two sides of concurrent programming we saw were preventing race conditions with mutexes and using condition variables to coordinate threads. Okay. Then okay. We spent a little bit of time on block devices. And where in memory we have addresses, we have byte addresses. Every byte has an individual address. You can retrieve an individual and modify an individual byte in memory, but you can't modify a bit. You have to read the byte, modify the bit, and write it back. Your block device is arranged in 4K blocks. There's older ones that may be a fraction of that, but we'll forget about that. If you want to modify, the 5th byte in a block, you read the block, you modify that byte, you write it back. Your unit of reading and writing is no longer 8 bits, it's 32K bits, or 4K bytes. And on top of that, we have this file interface, which is pretty similar across a lot of operating systems. We focused on the Unix interface, but you've got a hierarchical path name. You've got files which are, you've got a hierarchical file name that's made up of directories and a leaf. So if it's a file name, that leaf is the final name of the file. Once you open a file, you're able to read from it or write to it. We can a file on disk, you can jump around when you're reading from it or writing to it because it's this static thing. Unlike a connection on the network, you can't skip back in time when you're reading from a network connection, when you're reading from the keyboard, something like that. Those keys were typed, a minute ago. They're not coming back. If I store a file on disk, there's no reason I can't start reading from the beginning all over again. Or for some database-like applications, I can, skip around and read different parts. With the simple Unix interface, the old-fashioned Unix interface, you have to do what's called a seek to move this file pointer around. The file pointer is how internally the the operating system keeps track of where you are when you're reading a file from beginning to end. Or any modern operating system has some version of a system call that lets you just read a chunk from the middle of the file by specifying the offset. But the key thing, which you probably noticed in Lab 4, is that you're translating between byte offsets. Well, I guess there's two things. One is that you need metadata. You need directories. You need data describing a file so you know what blocks are in a file. You need some way of translating from the namespace, from /temp/file.txt to a set of blocks on disk that's holding that file. And then, conceptually it's quite simple, but it's a bit of a pain in doing it in the lab, is figuring out exactly which bytes in these, translating between this block structure and the byte granularity that your read and write operations work at. So and in particular, we saw Lab 4 where we saw two key structures. One was the inode, which describes a file or a directory. It has things like the mode field that indicates the type and permissions. It has the length, and it has pointers to each of the blocks in the file. In a more realistic file system, this would be more complicated so that we could handle files bigger than 1,000 odd blocks, but the concept is the same. We've got some mechanism given an inode that we can find all the blocks in the file. And then, well, in the object. And some of those, each object has the same structure. If it's a directory, it doesn't contain file data. It contains an array of these directory entries. And so we can search in that array to find an entry that we're looking for. And so from the point of view of the file system, the key operations are really, well, the ones we implemented were get the attributes of an inode, list the files in a directory, read data out of the blocks of a file, and actually we had to translate a path to the inode that path refers to. That was the basis of everything. If you add a few more things, add the ability to write to a file, a few other things like changing the permissions and the name, then you actually have a fully functioning file system. Quick question, did anyone who got Lab 4 working, did anyone try running Lab 4 Fuse? Okay, because you you should be able to do it. I think you can do it with make mount, and it will create a directory, and you'll see the contents of that disk, in the directory. If we had written write methods, then you would actually be able to, yes.
So like when running the mount command on lab4, it does like create directories and files. Inside of those files, it's just like a random string. Is that okay?
Yes. Yeah, it doesn't create them. It exposes the files that are in that image.
So what does that mean, like the context that you saw?
They are random numbers that my file system generator created, so that, and the Gradescope grader has an exact copy of those files, so it can figure out, because they're random contents, it's pretty accurate at saying, oh, you have bad data starting at offset 4096 in your file, which is often really useful to know, because then you kind of know what mistake you made. But yes, there's a Perl script, there's a Python script that generates the files, and it's just picking random numbers, and or actually random characters out of a specific set of semi-writable, semi-readable characters. But yeah, it's if we had implemented the write function, which would be fine if there was another 2 weeks in the term, then you would actually be able to copy files there, and and compile them, edit them, whatever you do, unmount that, copy the file somewhere else, the image file somewhere else, mount it, and you would see the files that you had modified. It would be, with a bit of effort, you could probably create a Lab4 file system on a USB drive, and mount it on one computer, put files on it, then mount it on another one. So yes, it's right now it's working. Once you get it working, it works when you run Lab4 Fuse as a normal read-only file system. Oh, so the reason for that is, yeah. So block 0, there's really no super block for this file system, because there's no configurable parameters. Like normally the super block will have a number of things about how big the disk is and like what options you set it up with. There's no options here. However, if it was writable, you would need an allocation. Well, so block 0 is reserved just because basically most of the mistakes that you make that give you a bad block number give you 0. So I wanted to put an assert on reads and writes of block 0. And then kind of like, there's no reason why page 0 couldn't be writable in Linux, except that it makes it much easier to debug if accessing a null pointer crashes instead of doing the wrong thing. And then block 1 is the allocation bitmap. So if it was a writable, if we implemented write handling, we would be using that to record. We would be updating that as we allocated blocks, and so that means the next available block is 2. So we put the root directory there. That's actually it's actually a fairly common thing in file systems, is to basically say, this arbitrary number, usually a low number, is where everything starts. Yes.
So I think Linux usually uses ext4 and Windows NTFS.
Yeah.
The file system that we designed, what is it most similar to?
It's sort of it's most similar to ext2. And so the file structure and the ext4 has evolved both the file and the directory structures. So, and both of them support long file names, which, conceptually isn't all that much different from this, except that you have to have lots of, you need code that jumps over, that can skip through byte by byte and so on. But ext4 and NTFS both use essentially run length encoding instead of individual node pointers. So they'll have, instead of individual block pointers. So they'll have a record saying, block, block 20 plus, blocks 20 through 25. And that would be a single entry. And since blocks tend to get allocated consecutively, that takes up a lot less space, but uses a good bit more code. ext2 has this organization, except that it has the tree of indirect and double indirect blocks and so on, so the inode can be much smaller. Yeah, actually, it's, and then both ext4, well, ext3 and ext4, as well as NTFS, are journaled file systems. So unlike back in the 90s when I used ext2, if your computer crashes, it's very unlikely that you'll lose a bunch of data. Okay. Now, the last thing we talked about was permissions, and I'm actually going to go back and talk about what's going to be on the exam and what's not. So I think I'll have room on the board for permissions once I erase some stuff. Okay, so I think that conceptually understanding what's going on with the stack frame, I think, is an important thing. But honestly, being able to work out the details of it is maybe, not as important as some of the other parts of the class. So, just understanding that the stack is the entire basis of being able to context switch between programs. It's actually, there are some very old computer science papers where it can be very hard to understand them until you realize that they weren't talking about a language that used a stack, and they're describing things in a way that wasn't reentrant and didn't have any idea, so your code was basically just jumping around from one place to another. It's, it may have had, subroutines, but it might have as well have had a bunch of go-tos. And it's, it's very much a difficult context switch to try to understand. People writing about programming before they discovered that you could have local variables, you could have per function arguments, you could have this very reasonable function abstraction, and the way you do it is through the stack frame. Okay. So I think, okay, so going back. Yeah, you've seen it 3 times already. You're going to see the compiler question again. Hopefully everybody can get full marks on it this time. We got close in the last in the last quiz, but I think I guess the reason I think this is fundamental to this class is it's understanding the relationship between a slightly higher level language that you're writing things in and the actual hardware things underneath. We don't actually, unless you're, if you're writing code for a CPU that costs more than 25 cents, it's unlikely that you'll be actually writing assembly code or more than one or two, in a very rare case, more than one or two lines of it. But understanding this conceptual relationship, I think, is important. And one way of looking at it is that if you understand that question from the quiz, you've got a pretty good understanding of how pointers work and how the equivalent in higher level languages work. They may call them references, they may prevent you from shooting yourself in the foot, but again, that's what's going on when they translate your C++ or Rust or Java code into instructions. And that basically we have these elaborate high-level languages, and they're translated into these painfully simple low-level hardware instructions, and that most of what's going on in the high-level language is lost. The CPU doesn't know that this is a pointer to a certain type of structure. It doesn't know anything like that. We're adding numbers, we're reading from memory, and if those were correctly generated by the compiler, then they're doing the right thing. And if you had written, code that wasn't accessing things right, hopefully the type system would have prevented it from compiling. I think we'll have, I'm not sure if I'm going to keep it in or not. I think we may have a tiny version of the page fault question. I've got to decide if that will make it too long or not, but not, if it is, it'll be about a third the length of the one in the midterm. It may not be reasonable to get it down to that point. We will definitely have a question on condition variables. On concurrency with mutexes and condition variables. And so the way it works is really quite simple. When you wait on a condition variable, it unlocks the mutex and it goes to sleep. And then well, in fact, you implemented this in lab 3. You've got a queue, just like a mutex has a queue of threads waiting for it. You've got a queue of threads waiting on the condition variable. I'm thinking of it, in the homework, there was never more than one thread waiting on it. And when you signal that condition variable, it pulls the thread off and it wakes it up, which is pulling it off and making it runnable. But it has to lock the mutex before it returns. And so that logic is, that's, that's the logic you need to, to understand, to be able to work through a problem like the homework 6 one, which is, being a homework, it's a little too long-winded for the exam, but there will be something. Okay. Okay, for the file systems are going to be covered on the exam, and you'll have something like homework 8. Basically, given, which the solution to that should be, went up on Piazza this morning. Sorry to anyone who was late on it, but it's, I think everybody else wanted to see the answer. And the idea is, given, well, is basically, what is your Lab 4 implementation doing? What blocks do you have to read in order to translate from, to find the inode corresponding to a particular path, and then to read some data from that, from the data blocks. Although I would have liked to do a file write question, we just haven't covered it this semester, so there won't be one. And finally, there will be a question about file permissions. I mean, these are pretty easy. Does anyone remember why, I mentioned that, these permissions aren't all that expressive. Can anyone think of a case? Does anyone remember a case where you might have some set of, access rules that you wanted to implement, but you could not do them in Unix permissions. Yes. Yes. If you wanted one person to have if you had 4 different users and you wanted one person to have no access, one to have read only, and so on, then you can't do it. There's only 3 sets of permissions here: owner, group, and world. As a matter of fact, if if you had if you had 6 users and you wanted to lock out 2 of them, give 2 of them read only and 2 of them read write, you can't do that either. That's only 3 sets of permissions, but there's only one owner for the file, so this doesn't work either. It turns out it's good enough for most things, and we no longer use it for, it's not the same as, 20 years ago you would all be logging into login.ccs and we'd be using permissions to to keep people from, to be able to show other people your files or keep other people from seeing your files. Nowadays, I assume 90% of you have never created a file on the Curry, shared machines. Maybe 95%. So the permissions end up getting used mostly as part of an overall strategy to isolate different subsystems, basically to do defense in depth, to try to isolate parts of the computer from each other so that if an attacker breaks into one part, they can't hop to another service and attack that as well. Yeah, basically the internet was the worst thing that ever happened for computer security by far. All right, so yeah, I covered a few other things which won't be on the exam. So we won't be talking about networking on the exam. We won't be talking about virtualization. There's probably a couple of other things that I covered. You know, except to the extent that block devices live underneath the file system, we won't be talking about them on the exam, or direct memory access and various hardware architecture details. But I think that wraps up most of what we've talked about in class and what's going to be covered on the exam. So I guess I'll just open things up for questions for the rest of the class period. Yes?
Are the exam questions going to be, again, more related, or are they going to be not similar to labs? Because obviously we're not creating this, but is it going to cover a lot of the material in labs?
Not. No, I mean it won't cover it will cover lab material to the extent that other homeworks have, for instance. So, you know, this one, it's really a different question from the lab itself. You know, the lab, you're down in the weeds with the individual instructions. Here, it's, here's the, 6 or 7 instructions. How do we do something with them?
So I guess that's
I'm sorry?
the exam questions we've had in the past have been analogous to the homework problem.
Yes.
Is there, like, I guess, a permissions homework? I know that.
I posted a solution to a prior semester one, which isn't quite what I would have given out, but it does, I think, cover a lot of it. Yeah. It's with the other homework solutions. It turns out there's also 2 solutions to homework 6 because I forgot that I had already posted a solution in Piazza comments. So hopefully, I think they are slightly different, but again, it's the sort of thing that there's multiple ways in which things could execute. Um, if an answer is consistent with the programming logic, it's correct. If it's impossible from the programming logic, it's wrong. Yes?
Do you think you can post lab solutions as well? Just because it might help me understand
Lab solutions. I'll see what I can do. I mean, I'm not sure because mostly the labs are just the code. But I will think about that. Other question? Yes.
Will there be any extra credit?
Extra credit? I tend not to do that, although actually that would be the best way to do it. Yeah, there will be an extra credit question. There'll be an extra credit question, which is what number did I write on the board during the lecture? 17. It'll be worth a point or 2. That way I don't have to make all the questions, 24 points or something like that. Other questions? Yes. I think there'll be 4 questions, or maybe I'll do, 2 half questions, and make it 5, because really it's going to be of a similar, we've got 2 hours instead of 100 minutes, but I'm, shooting to make it not much longer than the midterm was. Yes.
So anything on the first midterm might be in the final except for maybe the network virtualization, right?
Oh, let me, yeah. Okay, the fork and file descriptors, no. And I really should have done a homework on that because the page table, no. The virtual memory, there might be a very short version of it, but not the extended remix like this. Although the trouble is, I'm not sure if this is only 5 instructions, and it's still, you saw how long it took. I may have to, although if I reduce the number of pages involved, it may, put all the code on the same page or something. It might make it shorter. What else? Any feedback for the course? Besides, yes, the management of this course is always a little disorganized, and we're clearly missing some homeworks. We did get all 4 labs out this semester, which is better than usual. Any suggestions for improving the labs? Yes. Okay, more. Yeah. So spend more time on C at the beginning of the class. Yeah. I think, and I may have gotten a little too comfortable because lab 1 was, very straightforward. It didn't have any, you weren't building any data structures and stuff. And so without too much effort, most people were able to do pretty fine. And the lesson I took away from that may not have been the right one, because then we start doing more complex things, and it wasn't necessarily so fine. Yes. Yes. The labs lab 0, where you start your VM, you commit a file on GitHub. That should have been, especially for an undergrad course, because, let's face it, you're undergrads, you're not going to start working on the assignment until a few days before it's due. I just, I can't expect anything else. So, doing that will help flush things out. Also, I am regretting ever posting anything about VS Code. I think that, that, there's definitely some people here who are very familiar with it and fluent with it and are able to set up their environments. But, providing guidance for people to set up an environment that the instructor and the TAs aren't fully fluent in doesn't lead to good results. So either we need to, learn more about VS Code, or just, propose an easier way. And if you want to do VS Code, you're on your own. Actually, what are people's reactions to that thought? Do you think that's a good idea or bad idea? Yes. Mm-hmm. Okay. It does seem like if you can get it working right, it's a very good thing. I'm nervous about recommending something that I'm not able to help people get it set up right. I'm not about to try and teach everyone how to use, Emacs remote access to your virtual machine. That's, time has moved on. My programming environment hasn't, but I'm not going to inflict it on other people.
The login CSS ain't bad.
What's that?
The login CSS isn't bad.
Okay. Oh, actually running on login.ccs. Yeah. Mm-hmm. Yeah. Yes.
Why do you prefer Emacs over them?
Those are fighting words. Anyway, but yeah, my contributions to GNU Emacs got totally rewritten long ago, so my name's no longer in there.
Do you not just use like WSL to run the code?
That would work for just about everything except, well, actually it wouldn't let you use Fuse on Lab 4, although honestly, I've tried to, in previous semesters, I've had people using, Fuse early on in that lab, whereas here, I almost haven't mentioned it to try and get people through the testing. And I really don't know how well it would work with the thread switching, but my experience is it's actually a pretty good environment. So it might be worth some time, getting the um, you know getting seeing if we can make things work there. Yes.
I actually I use WSL for all the lab. I managed to make it work for lab 4.
Oh.
When I tried using Fuse first, I got like a forbidden error.
Yep.
It said something was forbidden, so I did WSL dash U and got rid of it.
Oh. Okay. That's thank you for the information that you actually can, and so actually the thread switching logic worked for. Okay, what's very interesting about that is it turns out that I've mentioned how compilers, everyone writing a compiler has to agree how you pass the arguments, what register the return value goes into, and so on. There's one answer for Windows, and there's a different answer for Linux. So in particular for Linux, it passes the first 4 or 6 arguments in the a certain set of registers. For Windows, it passes them in a different set of registers. I guess that WSL uses the Linux binary interface because it works. Because if the threads work, it's working with my assembler code, which assumes which assumes the Linux ordering. These are the sorts of things that when you're underneath the level of the programming language, the way the programming language is implemented makes a difference, and it changes from, in some ways.
Yeah, I was going to say the same thing. I use WSL for all the labs.
Okay.
I think it's also easier to use VS Code because you're not.
Yeah. Yeah. That's interesting because there is a Fuse replacement for, well, okay, honestly, my main reason for not wanting to go native is probably, issues with debugging in the Mac environment. You either go full Xcode or, we have to sort of support both GDB and LLDB as debuggers. But I'll definitely think about it. Other, yes. Yeah. If I haven't done the calculation yet, but the quiz grade will bring up your, question 1 midterm grade somewhat. And if you already did well on question 1 on the midterm, since everyone pretty much took the first quiz, then, I'll bump that credit over onto a homework. Of course, I got to get everything into a spreadsheet and go and try and do this. But all right. Any questions about anything related to the course? Yes. Oh, I forget. Is it 3700? I'm sorry? Yep. Okay. That's, yeah. This is pretty much the only undergrad class I teach, and it's they keep changing the classes on me. At least this, this and 5600 haven't changed. But yeah, there's there's a bunch of interesting stuff in networking. Actually, when I was in industry, the first half of my career was in networking. Um, Unfortunately, my networking knowledge is sort of state of the art as of about 2001. There's a lot that's happened since then, but pretty much every big system nowadays has a large amount of networking at the core. No. I just put it's in. Where's Hertig Hall? It's somewhere over near towards Curry, right? If so, yeah. So Hertig. Let me write it in great big letters. So it is from 10:30 to 12:30, not at 11:45, not at 2:50. In Hertig 130, which I probably should stop by after class so I can just see what it looks like. And the I think I'm not allowed to have projects due after the exam, so I gave everybody a whole bunch of slack hours. But actually, the based on people's progress on Gradescope and stuff, I mean, how many people have finished the Lab 4? How many people thought it was too hard? Too easy? Somewhere in the okay? Yeah. It's so, and I definitely tried to improve the the greater error messages this semester, so it would do a better job of telling you what went wrong. So hopefully that will fix, as opposed to finding out that it read the file and got a checksum error, that isn't all that useful. So, all right, it's been a good semester. I'm glad to have had you, and good luck on the exam.